Nevada's in the throes of an epic water crisis, so much so that the feds have issued a water shortage declaration.
What is Nevada doing right now to make cuts amid the region's water crisis?
Here in Nevada, we're taking bold, drastic steps to address the issue. One example is AB 356.
America is running out of water, and one proposal sounds almost absurdly brilliant.
Big step here to mitigate the water crisis right now in southern Nevada.
Pipe seawater from the Pacific, pump it over mountains, and flood Nevada's deserts to create a brand new inland sea.
We've got the biggest ocean in the world, so why aren't we using it more to desalt it and drink it?
It could stabilize the Colorado River, store renewable energy, and power the Southwest for generations. But beneath the bold engineering lies a darker reality. What looks like salvation may be a slow-motion disaster. Engineering Nevada's ocean ambition. In 2025, the Colorado River Research Group released a devastating report stating that the Colorado River reservoirs are now facing a crisis. This river supplies water to 40 million people across 7 states, 30 tribes, and Mexico, and generates billions of dollars in agricultural output, supplying the U.S. with fruits and vegetables in winter. For the past 2 decades, it has been going dry. Reservoirs that once held 4 years of river flows are now more than 2/3 empty, and if 1 or 2 more years go by without rainfall, their primary storage units, Lake Powell and Lake Mead, would enter a critical threshold. These lakes, especially Lake Mead, serve as the backbone of the water supply for the American Southwest. In fact, reports project that by 2026, Lake Powell will sit at just 48 feet above the minimum power pool, a threshold that if the lake falls below, the Glen Canyon Dam would no longer generate hydropower for millions, and its ability to release water downstream would be jeopardized. To prevent that scenario, federal and state authorities have put emergency measures in place. Lake Powell will follow planned release schedules that balance water supply needs with hydropower generation. Downstream, Lake Mead remains in a Level 1 shortage condition, which triggers mandatory water reductions for Arizona, Nevada, and Mexico. Together, these coordinated actions would reduce stress on the system and prevent both reservoirs from dropping to dangerously low levels. But these are short-term fixes. Current guidelines are set to expire at the end of 2026, and officials are urging the 7 Colorado River Basin states to reach a consensus on post-2026 operating rules.
Yeah, and this is a big deal for us here in Arizona because we get about 30% of our water from the Colorado River. Negotiators for the states that tap the river, including us here in Arizona, all in Las Vegas this week, with the water source for some 40 million people hanging in the balance.
If the 7 basin states fail to reach a new consensus by 2026, the river would revert to operating rules from the 1960s, which experts call a nightmare scenario, incapable of dealing with today's drier reality. However, it is not just the basin facing trouble. Underground, the situation is even more dire. Groundwater aquifers, which communities and farms rely on when river flows drop, are disappearing even faster than surface water in Lakes Powell and Mead. Despite this, groundwater is poorly managed across the Colorado River Basin and is largely excluded from negotiations over how to share and conserve river water. In Arizona, for example, much of the state has no groundwater regulations, leaving wells running dry and aquifers that would take centuries to recover naturally. Even in areas with some regulation, aquifers continue to decline, and scientists warn that relying increasingly on groundwater to offset river cuts will only worsen losses. Experts stress that surface water and groundwater are interconnected. What happens underground affects rivers and reservoirs, and vice versa. Yet federal and state laws focus almost entirely on surface water, leaving the hidden underground crisis largely unaddressed.
Rural Arizona is demanding solutions to protect their water. We will deliver for them, and I'm urging legislators to listen to the voices of rural Arizonans and do the right thing by passing this common sense legislation. Our futures depend on it.
Without coordinated management of both sources, the Southwest risks running out of water entirely. State negotiators may agree on cuts to the Colorado River, but implementing those cuts locally will almost certainly push communities and farmers deeper into groundwater depletion, compounding the crisis and threatening the region's long-term water security. But what if water engineers have found a solution to this? A very ingenious solution that could solve this water crisis once and for all. Researchers have proposed capturing seawater from the Pacific Ocean off the coast of California, desalinating it and pumping it into arid valleys. In this case, it is Nevada's valleys, the driest of all 7 states affected. But it doesn't stop at supply. The goal is to create one or more giant artificial lakes, an inland sea, in places like Panamint Valley, Big Smoke Valley, and Amargosa Valley. The first thing that would puzzle anyone is, how does water from the Pacific Ocean get into Nevada? The answer to that is surprisingly straightforward: pipelines. But these aren't just ordinary pipelines. They have to thread across deserts, navigate through mountain ranges, and traverse private and protected lands. Instead of cutting directly through sensitive ecological zones or requiring extensive land expropriation, engineers suggest routing the pipelines along existing transportation corridors, such as Highway 95 and old railway lines. By sticking to these pre-established rights-of-way, the project minimizes conflicts with federal environmental protection laws, land use regulations, and the intricate patchwork of state and private property rights. It also simplifies the installation of pumping stations, maintenance access roads, and the necessary power transmission lines, which can all be integrated into areas with existing infrastructure. From the coast, water would cross the Mojave Desert and reach central Nevada. Even with an optimized route, gravity remains a big issue. The valleys lie between 1,000 and 1,700 meters above sea level, bordered by the Sierra Nevada and the coastal mountains. Lifting water on this scale is physically demanding and energy-hungry. Initial estimates suggest the pumps would require roughly 6 gigawatts of continuous power. To put that into context, the most iconic hydroelectric project in the United States, the Hoover Dam, produces about 2 GW at full capacity. This means that lifting the water would require the equivalent of 3 Hoover Dams running non-stop. Now, if the project relied on fossil fuels like coal, oil, or natural gas to power the massive pumps needed to move billions of gallons of water over mountains and across deserts, it would release huge amounts of carbon dioxide and other greenhouse gases. Even though the plan could help solve the water crisis, relying on fossil fuels would weaken its environmental and climate-friendly claims, potentially turning it into a major source of climate pollution. But what if this same project could also generate its own power and solve the energy problem at the same time? Making the desert a giant battery. By 2030, Nevada is likely to reach its goal of 50% renewable energy, while California is reported to have 42 gigawatts of installed capacity. These 2 states are leading in solar power generation, and researchers believe this could be the solution to the project's pumping issue. The solution is a system with an underlying mechanism called pumped storage hydroelectricity. When electricity is plentiful and inexpensive, primarily during midday hours when solar output across California and Nevada peaks, the system uses that surplus power to run massive pumps. These pumps perform 2 related tasks. One is logistical, moving desalinated water inland toward Nevada's arid basins. The other is energetic, lifting large volumes of water from the inland sea itself, which acts as a lower reservoir, into a second reservoir positioned at a significantly higher elevation. In doing so, electrical energy is converted into gravitational potential energy, stored not in batteries or chemical bonds, but in water held in reserve above the desert floor. The energy generated by the system appears only when this process is reversed. As solar production collapses in the evening and electricity demand rises, water is released from the upper reservoir and directed downhill through pressurized pipes. Turbines embedded along this descent convert the kinetic energy of falling water into electricity, feeding power back into the grid during hours when prices are highest and supply is most constrained. The electricity produced is hydroelectric, dispatchable on demand, and carbon-free at the point of generation. But because of mechanical losses in pumping, friction in pipelines, and turbine inefficiencies, the system returns less energy than it consumes, typically on the order of 70 to 80% of the original input. The remaining energy is lost as heat, an unavoidable feature of storage at this scale. There is also a financial logic embedded in this design. Electricity prices tend to collapse during periods of excess solar generation and spike after sunset. By consuming power when it is cheapest and selling it back when it is most valuable, the project attempts to offset part of its own operating costs. However, the engineering assumptions underlying this model leave several critical challenges unresolved. The scale of energy losses becomes significant when multiplied across gigawatts of continuous operation. Even a 20% loss translates into vast amounts of electricity wasted daily. Unlike traditional pumped storage facilities, which cycle the same water repeatedly between two reservoirs, this system must also permanently move water inland, creating a constant energy draw that persists even as market prices rise. Also, the physical infrastructure required to support this operation causes additional strain. Solar overproduction occurs in specific geographic zones, while pumping stations, reservoirs, and demand centers are distributed across long distances. Transmitting large amounts of power between these points requires extensive grid upgrades, new transmission corridors, and regulatory approvals that are often slower and more expensive. Environmental and geological uncertainties also accumulate over time. Repeatedly cycling massive water volumes through newly constructed reservoirs increases risks of seepage, evaporation, land subsidence, and induced seismicity. In arid climates, evaporative losses alone can erode storage efficiency, especially over multi-decade timeframes. These effects are not easily modeled at full scale and tend to emerge gradually rather than immediately. There is also exposure to market risk. The economic viability of the system depends on persistent price spreads between daytime and nighttime electricity, continued dominance of solar generation, and limited competition from alternative storage technologies. Advances in battery storage, thermal systems, or hydrogen could compress those spreads, reducing the financial advantage of pumped hydro at an extreme scale. Finally, the system tightly couples two critical resources: water delivery and energy storage. During periods of energy scarcity or price volatility, operational priorities may conflict. Decisions about whether to release water for power generation or retain it for long-term water security introduce political and operational pressures that conventional power plants do not face. The engineering design assumes these trade-offs can be managed, but it does not eliminate them. But even if the project is successful, how do people consume the salty seawater? The desalination dilemma. The transformation of Pacific seawater into a usable inland resource is possible through large-scale reverse osmosis desalination. Seawater is pressurized to roughly 1,000 pounds per square inch and forced through semi-permeable membranes, whose pore size allows water molecules to pass while rejecting dissolved salts, minerals, microorganisms, and most organic compounds. The output is split into two streams, one of low-salinity freshwater suitable for municipal and agricultural use, and another of concentrated brine, typically about twice as saline as the source ocean water. Facilities such as the Claude Bud Lewis Carlsbad Desalination Plant in San Diego demonstrate that this chemistry works reliably at scale, producing approximately 50 million gallons of fresh water per day through continuous membrane operation. That same facility, however, also illustrates the magnitude problem embedded in the inland sea proposal. Carlsbad is among the largest desalination plants in the United States and supplies roughly 10% of the San Diego region's water demand. The inland sea concept requires an entirely different order of magnitude. Creating and sustaining a large artificial inland body of water while also supplementing regional water supplies would demand desalination capacity not incrementally larger, but exponentially larger. Estimates suggest that offsetting even 10% of the Colorado River's current flow would require desalination capacity on the order of 14 times that of Carlsbad. At that scale, the system ceases to be a single plant and becomes a vast industrial complex composed of thousands of membrane modules, redundant pumping systems, and continuous chemical pretreatment operations. Pretreatment is one of the most demanding components of the system. Raw seawater contains suspended sediments, organic matter, microorganisms, and seasonal algal blooms that can rapidly foul reverse osmosis membranes. To prevent this, incoming water must be filtered, chemically conditioned, and disinfected before it ever reaches the membranes. At the inland sea scale, this pre-treatment infrastructure resembles a full chemical processing facility, requiring constant dosing of coagulants, biocides, and antiscalants, as well as continuous monitoring and replacement of membrane elements. Each additional layer of treatment adds cost, complexity, and operational risk, particularly when multiplied across dozens of parallel desalination trains operating without interruption. Alongside freshwater production, the process generates an equally large volume of concentrated brine. For every gallon of potable water produced, roughly 1 gallon of brine remains. At the scale envisioned, this waste stream becomes a central environmental constraint rather than a peripheral issue. Discharging dense brine back into coastal waters can cause it to sink and spread along the seafloor, increasing salinity to levels that stress or kill benthic organisms. Residual treatment chemicals and trace metals from pipe and pump corrosion can further compound these effects. Managing brine responsibly at this volume would likely require extensive dilution systems, offshore diffusers, or additional treatment processes, all of which increase energy use and infrastructure demands. Rather than treating this brine solely as waste, some proponents point to its latent mineral value, particularly lithium, as a potential offset to both environmental and economic costs. Lithium occurs in seawater at trace concentrations and becomes more concentrated as water is removed through desalination and evaporation. In theory, a system processing ocean-scale volumes of water could accumulate brine streams rich enough to justify mineral recovery, especially as demand for battery materials accelerates. This makes the project even more promising and shows that the inland sea could evolve into a strategic resource hub, producing not only water and energy storage, but also critical materials for the energy transition. However, the practical constraints are severe. Ocean-derived brine contains lithium at concentrations orders of magnitude lower than those in natural salt flats, requiring advanced separation technologies such as ion-selective membranes or solvent-based systems. These processes are energy-intensive, sensitive to fluctuations in brine chemistry, and largely unproven at the sustained throughputs implied by the project. More importantly, mineral extraction does not eliminate the brine. It transforms it. Lithium recovery leaves behind even more chemically complex residual streams, enriched in other salts and processing reagents, which must still be managed within a closed or semi-closed system. In a terminal basin or coastal discharge environment, these residues remain part of the same accumulation problem they were meant to solve. The Salton Sea's toxic legacy. The Salton Sea is a vast lake that was formed in 1905 when Colorado River floodwaters accidentally breached an irrigation canal and poured into the Salton Sink. The sea became a permanent feature of the desert, sustained not by a natural river, but by agricultural runoff from the Imperial Valley. Just like the proposed inland sea, this sea's origin also involved human-created seas in hydrologically terminal desert basins, which are dependent on engineered inflows for their survival. And that makes the Salton Sea the perfect case study of the future geochemical and ecological effects of such systems. In terminal basins with no outlet to the ocean, water exits only through evaporation, while salts and pollutants remain behind. Over time, they concentrate. At the Salton Sea, this process has pushed salinity to roughly 74 parts per thousand, more than double that of the Pacific Ocean. The ecological effects have been so severe that fish and bird die-offs occur repeatedly, driven by salinity stress, oxygen depletion from nutrient-fueled algal blooms, and disease outbreaks such as avian botulism. As organic matter decays in the increasingly saline water, gases like hydrogen sulfide are released, producing the well-known rotten egg odor that signals systemic collapse. The crisis has since expanded beyond the water itself. As inflows have declined due to upstream diversions, the Salton Sea has receded, exposing more than 100 square miles of contaminated lakebed. This dry playa contains decades of accumulated agricultural residues including arsenic, selenium, legacy pesticides such as DDT and other toxins. Desert winds loft this fine sediment into the air, turning the problem into a public health emergency. Imperial County now experiences some of the highest childhood asthma hospitalization rates in California, with multiple studies linking respiratory distress to dust emissions from the exposed lakebed. Critics argue that the Nevada Inland Sea is structurally vulnerable to the same outcome. Proponents emphasize a key difference. The source water would be desalinated seawater rather than agricultural runoff. But this distinction addresses only the initial condition, not the governing process. The proposed Nevada basins, like the Salton Sink, are terminal. Every gallon of imported water would ultimately evaporate under desert conditions, where annual evaporation rates are estimated at 2 to 3 meters. Even if the inflow begins as fresh water, the act of flooding a desert basin initiates chemical weathering. Water leaches salts, minerals, and trace metals from ancient soils and surrounding rock formations through direct contact and seasonal runoff. With no outlet, these dissolved materials accumulate, cycling through the water column and biological systems until the lake moves steadily toward higher salinity. Desalination defines the starting point, not the trajectory. The project's proposed energy storage function introduces an additional accelerator. To generate electricity, water must be cycled repeatedly between the inland sea and an upper reservoir. This constant fluctuation destabilizes shorelines, prevents the formation of durable wetlands, and creates bands of exposed, moisture-rich sediment vulnerable to wind erosion. More importantly, it increases total evaporative surface area. Instead of one large water body, the system would maintain two, both losing water to the atmosphere. The combined evaporation would concentrate salts more rapidly, pushing the system toward brine conditions faster than a static lake. The operational requirement to store and release energy thus directly conflicts with long-term water quality. The most consequential risk lies in permanence. The Salton Sea is extraordinarily difficult to remediate because it cannot simply be drained or abandoned without creating severe downstream impacts. A Nevada inland sea would pose an even larger challenge. The project commits future generations to continuous, flawless management. If, decades into operation, costs become unsustainable, infrastructure fails, or political support collapses, water deliveries could stop. The result would not be a restored desert valley, but a rapidly shrinking lake exposing vast expanses of chemically enriched sediment. Over time, those sediments, laden with concentrated salts, industrial residues, and treatment byproducts, would generate toxic dust storms on a continental scale. What begins as an engineered solution would harden into a permanent custodial burden, transforming the landscape into a long-term hazard that cannot be safely undone. With such a severe domestic warning, why would anyone propose this path? Proponents point abroad to nations that have seemingly defied their arid geographies through sheer engineering will. The pacesetter nations. Israel's national water carrier, completed in 1964, stands as the groundbreaking example of a nation using integrated engineering to secure its future. Faced with a geography where 60% of the land is desert and freshwater was concentrated in the north, Israel's goal was not a choice, but a necessity for survival and growth. The NWC is a gravity-assisted conveyance system that functions as the country's arterial water network. Its primary feat was lifting water from the Sea of Galilee, which lies at 213 meters below sea level over a total elevation gain of approximately 600 meters to reach the populated coastal plain and the arid Negev desert in the south. This system of pipelines, canals, tunnels, and massive pumping stations was a mid-20th century engineering marvel that could transport about 450 million cubic meters of water annually at its peak. The NWC's true genius, however, lies in its evolution. It provided the foundational infrastructure that later allowed for the seamless integration of other technologies. Today, it doesn't just move lake water. It is the backbone of a system that distributes water from large-scale wastewater reclamation, since Israel reuses about 90% of its wastewater, primarily for agriculture and coastal desalination plants. The carrier transformed Israel from a water-insecure nation into a global hydrotechnology leader, proving that a centralized, state-managed hydraulic system could defeat geographic determinism. On the other hand, Saudi Arabia created a different and even more extreme model. They created an entirely new water supply from the sea. With virtually no perennial rivers or freshwater lakes, the kingdom's strategy has been to master desalination at an industrial scale. It operates a vast network of over 30 major desalination plants, predominantly using thermal distillation, which produces potable water that is then pumped inland. This water is distributed through a 4,000-kilometer pipeline network to meet about 70% of the water needs in its cities, making it the world's largest producer of desalinated water. The ambition of this system is not merely to provide drinking water, but to enable life and economic activity wherever it is deemed strategically important. A vivid, almost surreal extension of this capability is the plan for the 2029 Asian Winter Games in Trojena, a futuristic city in the Neom megaproject. There, desalinated seawater will be pumped from the Red Sea over long distances and up into mountain reservoirs, where it will be frozen into snow for ski slopes. A stark demonstration of using engineered water to defy the natural environment completely. Saudi Arabia's approach shows that when financial capital is virtually unlimited and political authority is centralized, the technical hurdles of moving vast volumes of desalinated water can be overcome. In comparison, the proposed American Inland Sea project exists on a different plane of ambition, not merely in scale but in foundational purpose and context. Israel moved existing fresh water. Saudi Arabia created and moved new water for direct consumption. The Nevada plan aims to do both and also create a permanent evaporating desert reservoir that doubles as a continent-scale water battery for energy storage, all while potentially facilitating mineral extraction. Second, the political and regulatory landscape is not merely different from the international examples often cited, it is structurally hostile to projects of this kind. Israel and Saudi Arabia pursued their water strategies under centralized national authority, with unified control over land, energy systems, and water allocation. Decisions were executed vertically, justified by existential necessity, and insulated from subnational veto points. The American Southwest operates under a fragmented system of overlapping sovereignties governed by one of the most rigid and litigated water regimes on Earth. At the center of this complexity is the body of compacts, court rulings, treaties, and statutes collectively known as the Law of the River. Developed over more than a century, it governs the allocation of the Colorado River among 7 U.S. states, 30 federally recognized Native American tribes, Mexico, and multiple federal agencies. These rules were written during an unusually wet climatic period and are premised on water volumes that no longer reliably exist. Every major river basin decision is now contested terrain, where reallocating even marginal amounts of water triggers lawsuits, injunctions, and interstate conflict. An inland sea project would not sit outside this framework, it would collide with it. Any attempt to supplement, replace, or bypass Colorado River allocations would immediately raise questions of priority, substitution, and injury. States upstream would scrutinize whether imported desalinated water alters downstream obligations. States downstream would challenge whether new supplies justify reduced releases. Tribal nations, many of whose water rights are senior but unquantified, would assert claims to any system that reshapes regional hydrology. Federal agencies would be forced to adjudicate whether the project constitutes a new supply or an implicit reallocation of an already overpromised river. This governance burden is not ancillary, it is existential. The project requires decades of uninterrupted operation, stable financing, and continuous political support. Yet the law of the river has proven incapable of delivering long-term certainty even for existing infrastructure. Emergency shortage declarations, interim operating guidelines, and rolling renegotiations have become the norm. Embedding a megaproject within this environment means accepting that its water inputs, operating rules, and economic assumptions could be renegotiated repeatedly over its lifespan, often in response to crises beyond its control. Finally, the environmental legacy is intentionally risked. While Saudi Arabia accepts the high energy cost and brine output of desalination as a necessary trade-off, its projects don't intentionally create large, standing ecological liabilities. The Nevada Sea, by design, would create a massive, managed terminal lake in a delicate desert basin, knowingly embarking on a centuries-long chemical experiment with a high probability of leaving another toxic legacy. America isn't just playing technological catch-up, it is contemplating a project whose sheer amalgamation of engineering, political, and environmental gambles makes the formidable achievements of Israel and Saudi Arabia look like focused, linear solutions to straightforward problems. However, the nation isn't totally helpless. Instead of the single spectacular project, what if there is a way for America to secure its future through 1,000 smaller decisions? The safer routes. Rather than concentrating risk and capital into one massive piece of infrastructure, water planners increasingly favor distributed, decentralized sources that collectively add up to substantial volume while improving system resilience. These sources include harvested rainwater, stormwater captured during extreme precipitation events, air conditioning condensate recovered from large buildings, and treated graywater reused on site. Each source may appear marginal in isolation, but together they form a diversified portfolio that reduces dependence on distant imports. Federal policy has increasingly aligned with this approach. Agencies such as the Environmental Protection Agency and the Department of Energy promote non-potable reuse for irrigation, industrial cooling, and groundwater recharge, where ultra-pure drinking water is unnecessary. Los Angeles offers a working example. Instead of allowing stormwater to rush through concrete channels and into the ocean, the city is investing in spreading grounds, infiltration basins, and treatment systems that capture rainfall and direct it back into local aquifers. This water enters underground storage with minimal evaporation losses and can later be recovered through existing wells. Unlike a large inland sea exposed to desert heat, these methods capture water where it naturally falls and store it out of the sun. Water reuse represents one of the largest untapped supplies in the United States. Israel's experience demonstrates the scale of what is possible. Nearly all municipal wastewater is treated and reused, primarily for agriculture, freeing freshwater supplies for domestic use. The United States has begun to move in the same direction through direct and indirect potable reuse, in which wastewater is treated to drinking water standards and returned to reservoirs or aquifers. This process relies on advanced treatment trains that combine membrane filtration, reverse osmosis, and advanced oxidation to remove pathogens, pharmaceuticals, and trace contaminants. Research institutions and utilities are working to reduce the cost and energy intensity of these systems. The National Alliance for Water Innovation is supporting pilot facilities, including a project in Redwood City, California that integrates real-time monitoring and modular treatment units to lower operational complexity. Each cycle of reuse extends the functional life of a gallon of water, allowing it to serve multiple economic purposes before being lost to evaporation or discharge. Unlike supply expansion projects that chase new sources, reuse increases the productivity of water already embedded in cities and farms. Where desalination is necessary, researchers are working to limit its energy and environmental footprint. Ocean desalination, the backbone of the inland sea proposal, is expensive largely because seawater contains high salt concentrations that require extreme pressures to overcome. An alternative is brackish groundwater desalination, which targets inland aquifers with moderate salinity. Because these waters contain far less salt than seawater, treatment requires significantly less energy and produces smaller volumes of concentrated waste. Many Western states sit atop brackish aquifers that are unsuitable for direct use, but viable as supplementary supplies once treated. Supply expansion often obscures a more immediate opportunity, reducing losses in existing systems. Across the United States, aging distribution networks leak an estimated 6 billion gallons of treated water every day. Much of this loss occurs invisibly underground, the result of corroded pipes and delayed maintenance. Investments in leak detection sensors, pressure management, and pipe replacement can recover large volumes of water at a fraction of the cost of new supply projects. Equity considerations also shape the effectiveness of alternative strategies. Smaller, targeted interventions can address water quality failures that large infrastructure projects overlook. In Allensworth, California, a rural community long affected by arsenic contamination, a NAWI-supported pilot project is deploying automated treatment systems that require minimal technical oversight. These decentralized solutions improve public health directly, rather than routing new water primarily toward urban growth or industrial expansion. Together, these measures form a layered approach that distributes risk, adapts to local conditions, and evolves incrementally, avoiding the irreversible commitments imposed by a single monolithic project. Thanks for watching. Now check out the videos appearing on screen for more compelling stories.